In this video, we're going to go in depth in proving that Q is a field, and the purpose is to show you that this is it's a long process, and you really kind of have to check everything. So Q is a field, and then really I should say with the operations, so the usual plus and multiplication operations. So that is A over B plus C over D is find a common denominator, which is BD, and the multiplication operation is A over B times C over D is AC over BD. Now, technically, this is an operation defined on equivalence classes, right? Because we have equivalence classes of fractions, not just fractions. So technically, we have to check that these operations are well defined, which you're going to do in a homework problem. But with these operations, it's a field. So let's go through and check the properties. So to see or to check Q as a field, we show that plus and dot obey the additive, multiplicative, and distributive properties. Right, let's start with additive. So what we need to check is associativity of addition. So that's the first thing in our list of properties. All right, so we have to show that A over B plus C over D plus E over F is equal to A over B plus C over D plus E over F. All right, so let's work out the left-hand side first. So that's A over B plus C over D plus E over F. So that's A over B plus, take care of what happens in the parentheses first. So that's cross multiply to find a common denominator. And then we do the same thing. So it's going to be A dF plus B times CF plus DE over BDF. That's how you find a common denominator. And just so that we can compare this later, this is ADF plus BCF by multiplying our B in plus BDE over BDF. That's kind of complicated, but we know that adding fractions is a little complicated. Okay, that's our left-hand side. That's this part. Let's work on our right-hand side now. Let's do that, and I don't know, lavender. So our right-hand side. Our right-hand side is A over B plus C over D first, and then add in E over F. So that's AD plus BC over BD, and then plus E over F. And so then now we, again, multiply the F over. All over BDF. And lastly, we can multiply our F in. So we got ADF plus BCF plus BDE all over BDF. And sure enough, these are equal. So the left-hand side and the right-hand side are equal, so it's associative. But notice how that we had to actually go ahead and check. And it was not at all obvious with the rule for addition that this is true. Some of them will be kind of obvious, but in this case, it's not. All right, so it's associative, great. Now we have to check commutativity. So we need to take A over B plus C over D, and we need to check that's the same as C over D plus A over B. So that's our question. All right, so what we're going to do is I'm going to put a question mark through this, and we're going to work on both sides simultaneously. So the rule that I wrote above was AD plus BC over BC, or BD. And so this is going to be CV plus DA over DB. But multiplication of integers is commutative. So on the left-hand side, we're going to leave that alone. And on the right-hand side, I'm just going to move it's also addition is also commutative of integers. So within the numerator, we're going to reorder the terms, and within the denominator, we're going to reorder the terms. And that's perfectly okay, because in the numerators and denominators on their own, this is just integer operations, and we know we can do that for integers. So is this true? Yep. So is it commutative? Yep. We now have to check that there is a 0 element. This is called the identity. And I forget if in my list earlier if identity came before inverse or which order, but it doesn't matter, identity. So I claim that the 0 for the rational numbers is 0 over 1. Okay, so what we need to do is show that 0 over 1 plus a over b is the same as a over b plus 0 over 1 is the same as a over b. Now I'm really just going to show that this guy is equal to a over b, with the understanding is the other computation is the same. So let's compute it. The rule is you multiply, and then so you sort of cross multiply for the numerator, and the denominator is the product of the denominators. And if we work this out, we get a over b. Great. 0 over 1 appears to be the additive identity, but again, you have to check this other guy as well. And then we need inverses. So I claim that a over b plus negative a over b is 0. That is, this guy is the inverse for a over b, the additive inverse. So let's go in and check that. So what's a over b plus the rational number negative a over b? It's ab plus b times negative a over b squared. In this case, there's a b in both terms, so we could have just added the numerators, but notice if we just added the numerators, that is not the rule. The rule is for addition is this. So if this is our rule, then that's the rule we have to abide by. So I've written out exactly the rule. And so this is ab plus negative ab over b squared, but negative ab is the additive inverse of ab, so that's 0 over b squared. And I claim that 0 over b squared is the same as 0 over 1. Why? Well, fractions are the same if when you cross multiply, you get something true, and that is certainly true, so these fractions are the same. Great. So those are the additive properties, and we check that Q with this definition of addition satisfies the additive properties. Let's go to the multiplicative properties. This will be a lot easier in some ways. So we had associativity, namely a over b times c over d times e over f should be a over b times c over d times e over f. So let's just work that out. In this case, there's not going to be a lot of work, so I'll just put a question mark here. So we first take care of what happens inside. Let me write this slightly differently. Sorry, this is going to be a longer video because we have to do 10 checks. And then this guy is a times c over b times d times e over f. And so then this product on the left is going to be this, a times the quantity c, e, over b times the quantity df. And then we'll get a similar expression on the right-hand side. Now the numerators are just equal, and the denominators are equal. Denominators. As integer multiplication is associative. So Are these equal? Yeah, because the numerators and denominators, it's not even that the reduced fractions are equal. It's just that they're just equal as integers. So it's even better. We don't have to reduce anything. All right, so it's associative. Is it commutative? So is A over B times C over D the same as, oops, it's the wrong way. In the interest of time, we're just going to put a question mark through this. So the rule is this is A times C over B times D, and the rule is that C times A over D times B. But again, integer multiplication is commutative. So we're seeing that a lot of the properties from Q come from the fact that they're true for C, or for Z rather. So the numerator we can just rewrite as A times C, and the denominator we can just rewrite as B times D. So again, these are just equal as symbols. There's no reducing involved or finding an equivalent fraction. 7. Is there an identity? Well, I claim that the multiplicative identity is 1 over 1. So let's check that. 1 over 1 times A over B is 1 times A over 1 times B, and that's A over B. We also need to show that A over B times 1 over 1 is A over B. Okay, both of those work out. I checked them both this time instead of one of them. So we have a multiplicative identity. Great. All right, 3 more checks. So 8, we need to have multiplicative inverses for non-zero elements. Well, I'm in the multiplicative section, so just inverses. So if A over B is not the 0 element, then this tells us that A times 1 is not equal to B times 0. That is, A is not equal to 0. So A is a non-zero quantity. Thus, B over A is also a rational number. It makes sense to write that because A is a non-zero quantity. Now, if we multiply A over B with B over A, we're going to get AB over AB. And I claim that's 1 over 1. So why is that 1 over 1, which is the multiplicative identity? Well, this is because if we cross multiply, we get, of course, a true statement. So that's true. So since this is true, this quantity is 1, therefore B over A is the multiplicative inverse for Q. So you'll notice that here we have to be kind of careful with our fractions, and we don't actually get 1 over 1, we get something which is equivalent to 1 over 1, and we have to go and we actually have to check that it's equivalent. Okay, so those are all the multiplicative properties, and then finally we have to check that the multiplicative, well, we have to check the multiplication and the addition distributive interact nicely, and that's the distributive property. So we need to check left distributivity. And then I'll leave right distributivity to you because it's going to be exactly the same. So this is what we want to know. Let's just compute both sides as columns here. So we have to take care of the parentheses first. And on the right-hand side, it's just the addition rule, or the multiplication rule. I'm going to stop writing the dot when it's happening within the numerator and denominator independently. All right, and then we have to multiply, on the left-hand side, we have to multiply our a in. And then on the right-hand side, we have to find our common denominator. So I'm going to multiply the bf over. Ooh, did I make a mistake? All right, so technically I need to multiply by bf, but then I'm going to have to cancel a b somewhere. So I'm going to not use the rule because we know that really I just add an extra d on this one, and really we add an extra f on this one. So I'm going to cheat a little bit. Okay, but anyways, what we're going to get here is we're going to get ACF plus ADE over BDF. And then on the left-hand side, since multiplication of integers is distributive, we can distribute that in. And I'm going to not write parentheses because we know that it's also associative. And this is, of course, true, and so it's distributive. And 10, the other one, is exactly the same. So let me just write it down in the interest of having a complete thought here, but it's exactly the same. And so if we've learned something, we've learned that actually all of these checks are important and we have to apply the definition. I mean, I cheated a little bit at the end, but we have to apply the definitions as we have them. All of the checks are important, and there's usually some substance, at least, to all of the checks. There better be. We're checking that it satisfies the condition for being a field. And you'll have some more practice doing similar checks in class. We're going to do one more check in the next video, and then you'll have again more practice in class.